In this session, we're going to discuss combinational logic circuits, and this part will be dealing with the circuit optimization part. So, in this session, this part will be covered. We will take a look at the two-level optimization, map manipulation methods. We will skip this. I will briefly explain, and then we will move forward to multi-level circuit optimization. Why are we doing circuit optimization? Our main goal is to obtain the simplest implementation for a given function. That's it, because it's much more efficient engineering-wise. And optimization is a more formal approach to simplification because you need to use a specific procedure. Because we're trying to reach the optimum, which is something very challenging, right? Optimum means it is the best or best cost circuit, lowest cost circuit, or something like this. That's why. So optimization requires a cost criterion to measure the simplicity of a circuit. You need to have a measure for this. We have three different measures for this purpose: the literal cost, the gate input cost, and the gate input cost with nuts, where we count the number of nut gates as well. The literals are basically a variable or its complement. We call this a literal. And how many do they appear in a Boolean expression is the literal cost of that circuit. As you see here, it's pretty straightforward. You have 2, 3, and you have 8 here. That's it. And how about the next one? 2, 3, 3, 3. What's it? It's 11. And how about the next one? This is 2, 2, 3, 3. It's 10. Yes, it's 10. See, and which solution is best? Of course, this one has the cheapest cost. And of course, literal cost, cheapest literal cost. Otherwise, it could be different for other types of measures. If we count the gate input cost, how many inputs do we have to a gate here? I count these ones. That's it. So this is a 2 input AND gate, 3 input AND gate, 3 input AND gate. See, and they all connect to a 3 input OR gate, right? I'm sorry. So what you have here will be 3, 3, 2 coming from the literals. You see, it's 8 plus 3, 4 OR gate. So you get 11. What if you count the nuts as well? The inverted as well. B is inverted, C is inverted, and D is inverted. It means that you add 3 for this. Now you will have 14. Let's quickly calculate the other ones as well. So it's 2, 3, 3, 3 connected to a 4 input OR gate, which would make your gate input cost 15. I hope it is right. And what if you count the nuts as well here? How many nuts do you have? 1, 2, 3. No need to count this twice because you can take a wire out from this one. So it means that your gate input cost with nuts will be 18. That's it. And how about the last one? That one is 2 input, 2 input, 3 input, 3 input connected to a 4 input AND gate. That's what we have. We add all of them up and we will get the gate input cost, which is your 14. And how many inverters did we use? 1, 2, 3. No need for this one. No need to repeat. It is redundant. So you will have 17 as gate input cost with nuts. Which one is the best solution? Of course, the lowest one. So the first one is again the best solution, cheapest solution, we can say. So this is explaining us how we count the gate input cost here, but we already did this, I think you know this. We first count the number of inputs to gates, okay, and this is your gate input cost, and if you add the inverters you will get the gate input cost with nuts. That's it. Now the one above, the solution above and the circuit below are in fact doing exactly the same thing. It means that their truth tables are identical, right? They are doing exactly the same thing but have different implementations here. The first one is the implementation of this Boolean expression, and the second one, the one below, is the implementation of this Boolean expression. You can easily say that the first one is a better solution because it has lower cost. So when we're trying to do a optimization on a Boolean function, we choose some measure for this. Suppose that we have chosen gate input cost, but the question is, when do we stop trying to reduce the cost? How can I know that I'm already at the minimum? And do we know when we have a minimum cost? Is it possible? So for that purpose, you will rely on optimum or near optimum cost functions for two-level optimization. It means that we will rely on sum of products and product of sums forms that we discussed in the previous session. And we will also introduce a graphical, very practical graphical technique, which is called Karnaugh maps, for making two-level optimization easier. A K-map is a collection of squares where each square represents a min term. What we're going to do here is just writing the truth table in a two-dimensional, let's say in another two-dimensional platform. That's it. And the collection of squares is a graphical representation of the Boolean functions. And adjacent squares will differ in the value of only one variable. Remember from gray coding from the first session, right? All of the neighbors in the Karnaugh maps will differ by only one variable. That's it. The index, I'm talking about the index numbers. And you just combine the squares by the powers of n. Like if you have n variables, you will have some combining of squares to the powers of n, the size of 1, 2, 4, 8, 16, okay, vice versa. It's going like this. And it can also be viewed as a reorganized version of the truth table. I just discussed this, and a topologically warped Venn diagram is used to visualize in algebra of sets. That's also possible to visualize it. It helps us to find the optimum solution for two-level circuits. And it is also visual, which makes it very practical, and it is much faster than doing Boolean optimization, like with the expressions. It's hard using some axioms and some functions there. It's prone to mistakes, right? Because you can miss some simplification, or like maybe you will miss the consensus theorem. So instead of this, you rely on a practical visual method for this. And it provides the basis for large-scale optimization algorithms as well. Just the basis, of course. Here you see the two variable maps. You see this one. As you see, what you have here is the index number, where you have x and y as inputs. You have both combinations here, like both possibilities here, 0 and 1. And 0, 0 is your index 0, 0, 1, see 0, 1. Okay, then 1, 0 here, this one, and 1, 1 here, this one. That's it. They all differ by one variable in adjacent squares. And it is just a different version of the truth table here. What you have here as value will be located in their corresponding positions here in the index. That's it. In fact, we're just transferring our truth table into this K-map. That's it. Let's take a look at an example here. Now, as you remember, we can combine them in squares of 2. Like I can have 1 square, size 1, and size 2 squares here. Okay, so my size 1 squares are this one. Okay, this is this one. See, from the index. See, like this one, because since I'm talking about minterms here. So, and this one here, previous lecture, that's it. And how about I combine it like this, size 2, okay? It will give you x equals 1 and y is changing, so it's not dependent on y. You will directly say that this is x. That's it. It's the most basic one, representation for K maps. And let's take a look at another example here. Okay, the first one is like maybe you go for size 1 first, and you will end up with 0, 1. I think this one, and 1, 0. I think this one, and this one is this one. This is redundant. No need for this. So this is size 1 rectangles. And how about size 2 rectangles here? Then if you go ahead and have 2 rectangles like this, the first one is x, and the other one is, you see, y is constant here, and x is changing here, so it's dependent on y, and you just add the minterms. That's it. That's how we do sum of products representation that we discussed just in the previous session. And let's take a look at the 3 variable maps. The 3 variable maps has 8 squares in it. That's the idea, because they again differ by only a single variable in adjacent square. Just you need to be careful here. Your x located here, okay? It can be also in truncated form, and like you can also have them like this. You can have x, y, z as well, but pick one and stick to it. I suggest you do this. It's okay. You can also go ahead and have a structure like this. This is also correct, but this is also correct. Either form is okay. So the thing is, be careful. 0, 0, 0, 1. Be careful. This one is, because it's gray coding, it should be 1, 1 instead of 1, 0, and you put your 1, 0 here. See, you just need to be careful about this one, but no, don't worry, you will get used to it as you use them often enough while solving questions. So this will be your index positions here, like this, and their corresponding terms, minterms, you see, for each of them. You see, for example, let's take a look at one of them, right? Let's pick one of them. Let's say I picked this one. What is this? It is 1, 0, 1. Since it is a minterm, how should it be? X, y not z, right? So this is where my minterm is. Alternative map labeling is very useful. Okay, I don't do this because I'm pretty used to it, but as a start, I suggest you to label your map. It helps you to visualize or make the makes you faster while solving questions. You see, this part corresponds to where your x is 1, and this part will be your x naught. Okay, when you look at this, look at the row like this. That's the idea. And this is your y part. See, your y is always 1 here, and this is your z part here. When you look from this direction, so your z is always 1 here. This is easy when we're doing simplification with K-maps. So let's take a look at some examples here. Look at this one. This is how we place them. Sum of minterms, 3, 2, 4, and 5 here. Your 2 is right here, 3, and 4, and 5. You place them in their location. What about the others? They're zeros. we don't put them. No need to put them since we're working with min terms only. And the remaining ones will be automatically zeros. That's the idea. And again, the remaining ones will be automatically zeros, and your 3 is here, 4 is here, 6 is here, and 7 is here. That's the idea, to put them in their locations. So by combining squares, we're trying to reduce the number of literals in a product term. So one square represents a min term with 3 variables, of course in 3 variable maps, that is. If we combine 2 of them, then we will reduce them to 2, for example, if you have x, y, z, for example. If you cover 4 of them, it means that you can reduce to a single variable. And if you combine, let's say, all the 8 variables, it means that all of them are 1, right? So it becomes directly 1, just like connecting 5 volts to your LED or output directly. It's the same, no need for a circuit for this. Okay, let's take a look at an example now. The thing is, if we combine them as size 1s here, see, this one, the resultant expression would look like this, right? It's 2, no, there are locations. Okay, this one is this one, right? And this one is 0, 1, 0 is this one, and this one is this one, and this one is this one, right? So, okay, this is a matter, but we don't like this, so there can be better option here. You can also go ahead and do it with like this. Just this one is y. Not this one, I'm sorry. This one is YZ, right? This one. And this one is what? YZ naught. Your Z naught is happening here. Your X is changing. You cannot put it here. So, okay. And what about the best one? It would be, of course, combining the largest possible square. So your Z is changing here. You see, Z is 1 here, 0 here. So it's not dependent on the Z, and it also your X is changing here, 1 here and 0 here, so it's not also dependent on X. So I can say that your function is equal to Y in its simplest form. That's the idea with combining squares. So of course, the largest square, the better solution. That's the idea. So we discussed this. It's how we cover the squares should be in powers of 2, depending on the variables. That's it. But we should be aware that these parts are also neighbors. So we can consider this as a cylinder. You see, this one is very nice. Let me try to explain this to you by showing, hopefully. Let me, how can I do this? Okay. Okay. So look at this. Now, suppose that, okay, this is my truth table, right? So I just combine them together. And you see that they are located like this. It's like, you know, they are neighbors. Normally, the ones on the right-hand side and left-hand side, that's how you draw it. But when you combine them, in fact, they will be neighbors. It looks like this. Okay, that's the idea. And let me just... Okay, that's what it tells us here to understand how it is located. So I can say that this ones and these ones are neighbors. That's the idea with, seeing them as cylinders. Okay, because they are neighbors with each other. Now let's read off the terms for the rectangles shown here. Let's take a look at them. Okay, this one is, for example, let's take a look at this one. This one is what? It's you see, it's y, z. And how about this one? It is, what is this? It is, as you see, it's y naught. It's y naught, z naught. Oops, not z naught. It's y naught, x naught, right? This one, I guess, because it's changing for y, and this was for this one. And finally, how about the last one? This one. This one, what is this? It is, look at this, it is z naught, okay, the both sides, and it is also x naught. Okay, so this is how we read them. And what else? We have now size 4 rectangles here. The one in the middle is what? Z. And this one is what? It is y naught. See, this one is z, this one is y naught. What else we have here? And how about this one? Let's read together. What is it? It is z naught. See, this type of, because they are neighbors. And do we have more? No, I guess we have all of these read here. Okay, we can do something extra. No, it doesn't matter. So what is this, for example? It's pretty obvious. It is y. So this is how we do it. So you can use this for simplification as well. Try to cover all the ones by choosing largest rectangles possible. Don't forget this, it always works. So you first transfer this information of the truth table into a K-map, and you obtain this. When you obtain this, it is piece of cake. You can do it easily. This is your largest square possible for covering all those ones, in terms, so it would be your Z. And this smaller one, it's because it's not possible to cover this one in a larger manner, so that's it. And this one would be x naught y. This is how we use the K-maps for simplification. Now let's try to solve this together. So we first put them in their correct locations. I hope I don't make any mistakes. Let's solve it together. So we have x, y, and z here. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0 here. And what you have here should be, okay, I need to put each of them in their locations. So it's 0, 1, 2, 3 is, okay, 0. You see, I don't put it. Then 4, 5, I don't put it. 6 and 7, right? So I put them in their locations here. So I'm ready to make the simplification now. So can I use another color? No, it's not possible. So no, I cannot choose another color. Anyway, so let's try to get the rectangles as large as possible. How about this one first? See, I labeled this one as X, this one as Y, and this one as Z, right? So this one would be Z naught, you see, Z naught, plus what else we have here? I have this one, you see, I have this one. What is this? It is X naught, Y naught, good. And what else I have? I think this one, it is what? Plus Y and X, or XY. Maybe it should be better if I write it in standard order, right? XY. So this would be my answer to this simplification question. Next time I will solve this in a colorful way, don't worry. So this is how we make the labeling for 4 variable maps. Look at this. Now, again, we rely on gray coding here. Just be careful about this. You see, the 1 is located here, 0 0 0 1 1 1 1 0. And then we introduce something new, which is called W here. Okay, now our standard order looks like this, W, X, Y, Z. And your W is here, Y is here, I'm sorry, X is here, Y is here. This is how you make the labeling, and finally your Z is here. This is how we do it. And this is the same thing, but this time a single rectangle or a single cell will correspond to 4 variable minterms, 2 ones, 3 variables, and so on. Okay, the 16 ones will mean constant 1. That's it. Your 5 volts. So now let's try to write them together. Let's write this first. Okay, this one is pretty interesting, right? So they are all neighbors, you understand? So how can I again show it to you? Not only in horizontal dimension, in vertical dimension, they are also neighbors. Let me show it to you again. I hope it's okay. This one was for 3 variable maps. Imagine that they are neighbors, okay? But also, these are neighbors too. Like if you rotate it like this, they are neighbors too. You can imagine like this, like a sphere or something like this, okay? See? They become neighbors too in both horizontal and vertical axis. So that's why that's why these are neighbors on the corners, you see? And that one, this is, and what is it? It is Z0, X0, right? The one in the corners. And what else? Let's take a look at the others as well. The one in the middle here, what is it? What is it? It is Z, as you see, and X, XZ, okay, the one in the middle. And what else? Let's now do this one. What right here? What is this? It is Y W not. I think correct. Okay, because it's in the W not part. You see, so it's Y W not. Good. So, oh my God, yes, let me, okay, this is again, okay, it's a mess. Let me use another color here. Blue is maybe not good. So let's just make some examples here. That's it. So what is this one, for example, okay, in red? What is this? Just tell it to me. It is X not W not, for example. Okay, just a few examples together would be enough. And what about this, for example, a larger one, size 8, right? What is this? It is, as you see, Z. That's it. And what else do we have? If you like this, let's do it together. So what is this? It's pretty obvious, I think. It is X0, right? So wonderful. What else? Okay, what is this? So it is directly 1, right? This is how we do combining the squares on 4 variable K-maps. Now let's solve this example together, but this time I will try to make this on let me just write this in the notes so that it could be more colorful. Let me find the slide first. Okay, so it is What was the function? Let me check. I'm cheating from my notes here. Okay, thanks. So it's let me use white color. Okay, we're trying to do this w x y z here, which is sum of min terms 0, 2, 4, 5, 6, 7, 8, 10, 13, and 15, right? So this is what we're trying to do. So from the scratch, we can do it together. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0. This is your w, x, y, z. Okay, I need to put this truth table right here, so let's do it together. So let me put the ones in there. Okay, 0, 1, 2, 3, 4, 5, 6, 7. Be careful, 8 is here. 8, 9, 10, 11. I'm right here, but it is 0. See? 11. I'm here. 12, 13, 14, 15. You see? This is how place them in their correct locations. Very nice. So now I can combine those squares carefully. The largest possible ones, don't forget. It gives you always the much better solution. What is this? So it is, okay, let's make the labeling as well, because maybe it would help you. W, X, Y, and Z here for labeling. So it would give you what? This one, X naught, Z naught, the blue one, and the red one will be what? Plus. So it would be X, Z, and plus we have one more term or two. Are you going to do it like this? Is there a better solution? Yes, of course, there's a better solution. The largest possible is the simplest. You see, they're neighbors because of this cylinder, I mean the neighbor thing. So that's why. So it is, what is this? It is W naught and what else? It is W naught and Z naught. Hopefully it is correct, the green one. You also check it yourselves as well. It is W naught and Z naught, I guess. So I think what we did was hopefully correct. Okay, let's take a look at this. Okay, so the resultant function, the simplified function, should be this one. That would be your answer. Hopefully, I solved it correctly. Hopefully. Okay, now let's solve another one. This time this one. Again, I will move to board for this purpose because it's better if we use some colors here. So need a fresh board for this. Okay, great. So this time I'm trying to minimize W, X, Y, Z. Just sum of min terms 3, 4, 5, 7, 9, 13, 14, and 15, right? Okay, this one, this time. So I first put them in the K-map carefully. 1, 1, 1, 1, 0, 0, 1, 1, 1, 1, 0. So as you see here, W, X, Y, Z. This is your W, X, Y, and Z region. Let's put them. Okay, let's go. So it is 0, 1, 2, 3. See? 4, 5, 6, 7. Be careful. 8, 9, 10, 11, 12, 13, 13, 14, 15. This is how I place them, right? And now I will get rid of these because I don't need them. Okay, for min terms, I don't need them for min terms. That's the idea. So now let's combine the relevant squares here as large as possible. This is what we do. So now there is a very interesting property here. We will also see this as well. I love this. Okay, good one. We'll see how it goes. Look at this one. It's quite big, right? What is it? It is Z. Your F equals Z and what else? X. ZX plus. What else you have? This one, which is your it's W naught and X and oops, not X. It's not dependent on X, you see. X. No, it's X. Yes, correct. W X. And Y is the Y naught is same here, but Z is changing. See, Z is changing here, so it's not dependent on Z here. So another color, this one. So it would give you M plus W Y naught and Z plus another color. Let's use another color here for combining this one. It should be what? W X and Y, hopefully. And finally the last one, let's pick it as white, this one, right? So it would be what? It is W naught Y Z. So W naught Y Z. Okay, this one. So it's not dependent on X. Okay, good one. So the thing is, when you cover all of these, in fact, you don't need this one. You see this? You can remove it and everything will be perfectly okay. If you remove this red, if you remove this red part, you will still be covering everything. So it means that you need some additional procedures for finding the simplest solution, right? So we will discuss this. Don't worry. This is happening because of selecting the essential prime implicants first. We will cover this. Okay. So if we return to our question, it's like this. So what is this? I mean, that I just mentioned about a prime implicant is a product term obtained by combining the maximum possible number of adjacent squares in the map into a rectangle with number of squares of power of 2. That's what we're doing so far. And and it is called the essential prime implicant if it is only covered by a single alternative. That's it. Otherwise, they are prime implicants, but if it is covered by only one prime implicant, but no other, it means that it is a essential prime implicant. Now, let's try to show this to you. I will do it step by step. Maybe it would be better. Let me just move to board again, because, or maybe I should use another color, I guess. Look, I will use red here, so it could help. Now, get the largest possible rectangles here, but no matter what there's, what they cover, there can be redundancies. You don't care. This one, this one, this one, size 4. You see this one, and this one, and this one. You see, these are the corners. You have all of them, right? And they're given right here for you. Okay, this one. But which of them are essential? Look at this points, these cells. This one and this one are exactly covered by only one prime implicant and nothing else. See? All the other ones has alternatives. You see? Let's take a look at one of them. How about this one, for example? It is covered by this. It is also covered by this, you see, so it has some alternatives. Other ones has alternatives, but only this one and this one don't have any alternatives. So that's why I picked them first and then place the others. Okay, I picked them first, put them in their correct locations, done. Now I select whatever I like with minimum overlap. This one and this one, for example, and I will be done. That's it. My choices up to me. Now that's why we're having this here. You see how interesting it is in our previous example. I think you understood this now, hopefully. If you have a structure like this, see, what was it? It was like okay, 1, 1, 1, 1, 1. And it's 1 and 1, right? So let me just pick the prime implicant for, okay, this one is size 4, great. Then I use this one, and this one, and this one for the others maximum. But which of them are essential prime implicants? Which of them? These ones, right? This one is a prime implicant. This one is an essential prime implicant. This one is an essential prime implicant. And this one is an essential prime implicant. And I need to put them first. If you put them first, you get this. You see, that's the idea. And no need to put the largest square in the middle. That's why the solution looks like this. So this is another detail with the K-maps for finding the prime implicants here. It's an important concept. That's what the algorithms are using as well. Computer-aided tools are doing as well for sake of simplification. Now let's find all the prime implicants for this example. Okay, let's do it. For this purpose, I need a fresh board. So okay, my question is F, A, B, C, D, which is a sum of min terms, 0, 2, 3, 8, 9, 10, 11, 12, 13, 14, and 15. Who it is correct? Okay, so I put them in my 0, 1, 2, 3, 4, 5, 6, 7, 8. I'm sorry, 9, 10, 11, 12, 13, 14, and 15. Okay, it looks like this. So what I do is, okay, I'm trying to cover all of them with largest possible alternatives. Okay, this one, I guess. 0, 1. Oh, there's a mistake here. Sorry. Here we have, here is, look at this. It's 0, 1, 2, 3. We have them. Okay, 4. So I have these ones. Okay, good. So 3 as well here. And okay, next one is this one. So the other one is, I think, this one. Hopefully I'm doing it correct, right? Okay, so when we write them, nothing else is left. These are all your prime implicants, and it's as you see, it is A, and the red one is what? It is I'm sorry, the red one is, let me put the labels, A, B, C, and D, and the red one is D nut and B nut, P nut, D nut, and the yellow one is P nut and C, right? B nut and C, I think, right? P nut and C. Hopefully I did it correct. So which one of them is the essential prime implicant? As you see, this one is something special right here, because it's covered by only a single prime implicant. And of course the blue one, many. And how about the yellow one? Maybe it's also useful because it also covers this one. You see, it's a unique one as well, this cell, as you see. So all of them are also essential prime implicants in this case. Now another example we have here. Now let's try to solve this one as well together. It gives us a hint that there should be 7 prime implicants here. Let's try to solve it together. So new one, and your G this time. Our function name is G A B C D is sum of min terms 0, 2, 3, 4, 7, 12, 13, 14, and 15. Now carefully, let's try to do this again. 0, 0, 1, 1, 0. Okay, we have some space here. Okay, it's A, B, C, D. A, B, C, D. All right. Now let's put them in their locations. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay. Try to cover with large. This one is large enough. First one. And then what is this? It is A, B, right? And the other one is, what else? Okay. Do we have any size 4? No, no more size 4, I guess. I only have size 2s now. This one and this one. What are they? They are B, C nut, D nut, and the one above is A nut, C nut, D nut. Okay. How about some others? This one and this one. What are they? So they are B, C, D, and the one above is A nut, C, D. Okay. What else do we have? Okay. You have this red one. It is A nut, B nut, C. Good. So far we have 6 prime implicants, but one more is this one. You see these are neighbors, so it is A nut, B nut, D nut. See, so we ended up with 7 prime implicants. That's the idea of finding the prime implicants. Which of them are essential? As you see, this one is an essential one. This one. And what else? Do you see any more essential prime implicants? No. All the other squares are covered by more than one, at least 2 prime implicants. So the other ones depends on our selection minimizing the overlap. That's the idea. So if you're dealing with 5 variable or more K-maps, you need to use, because since we're working in the 2-dimension, I mean paper and pen, we need to have 2 different maps for all of them. So if you have a structure like this, for example, VWXYZ, or a function like this, for v equals 0, you need to have a K-map. For v equals 1, you need to have another one. But be careful, this one and this one will be neighbors as well. Just imagine that they are just sitting on top of each other. Let me just show you. So there's my camera, this one. So look, that's the idea. I mean, now, I mean, for example, v equals 0 is above this one, like this. So they become neighbors. You see, since they're sitting on top of each other. That's how we deal with combining squares in this type of K-maps as well. It's becoming hard to visualize it, but it is possible. So if you need to have, for example, 6 variables, maps for 6 variables, what happens? Then you need to have, suppose that you have u here as well. It's it's extras, and then you need to have 4 different ones, like for uv equals 0, 0, for uv equals 0, 1, for uv equals 1, 1, for uv equals 1, 0. You need to have a k-map, a 4 variable k-map, a 4 variable k-map, a 4 variable k-map for each of them. So when you're trying to minimize, now can you imagine? It has become pretty hard to imagine. Then we need to use some techniques like 𝐚𝐝𝐞𝐝 algorithm can be interesting here for minimizing some variables to a degree, maybe up to 7 or 8 variables, I guess. It's doing matrix-based manipulation, minimization. I will not cover here because it's not included in the slides here. And you can also use the Petrik's method for choosing the best prime implicants in this case when you use 𝐚𝐝𝐞𝐝 algorithm or something like this. But okay, these are extra. I will put other videos on them if I can find the time, but I will. That's it for now. So what about the don't cares and k-maps? These are also an important issue because sometimes either an input combination can never happen, or it can happen but the result is not important for you. So like as you see, it will either not happen or the output will never be used. In this case, you put an X in the truth table for those conditions, those input combinations, and you can use them later for your own benefit to reduce the complexity of your circuit. How can I use them for my own benefit? I can treat them either as zeros or ones due to my liking. I will abuse them, okay? I will abuse those X cells for my for my benefit. That's it. Let's see how we do it. Suppose that you have a particular circuit just giving an output for A equals 1 and B equals 1 and C equals 0. That's it. Cases like this case, A, B, not C case will give you 1. Otherwise, don't care for all of the remaining conditions other than this, it will give you X. That's it. In this condition, you can treat them as zeros or ones due to your liking. It will result in more efficient solution for you. Let's take a look at this example. It's very nice. This is a circuit that gives you or blinks your LEDs when you have an input for larger than 5 or more. That's it. So your LEDs will not blink if you have, for example, input BCD inputs as 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and 0, 0, 1, 1, and 0, 1, 0, 0. These will give you strictly 0 as output because it is lower than 5, right? And otherwise, they should give you 1 up to what? Up to 9, right? From 5 to 0, 1. Oops, this one is a mess. From 0, 1, 0, 1 to 9 should give you output 1. That's it. But how about the, values larger than 9, for example? Larger than 9, for example. How about 10 or more? You don't care because those inputs will never happen. Because since we're talking about BCD, binary coded decimals, so you put there, you fill there with X's like this. And it helps us while minimizing. Now let's see how it works. So if we didn't use x's and focused on only these ones, like you will end up with something like this, I guess. This one, and this one. This is what we see here as cost. This is pretty straightforward one, not taking x's into consideration. See, and its gate input cost is 12. It's obvious. But what happens if we treat those x's as ones due to our liking, right? 1, 1, 1, 1. I imagine them like ones, and I draw the circles now. Oh, it's possible. I can draw some large rectangles here and another large rectangle here, like a larger, okay, it's not very large, but still large enough. And this one here, see? And it's much more beautiful, giving you a gate input cost of just 7 instead of 12. So it's nice. Now, okay, we need to solve an example together. Again, I will use the board, and we have a hint. Use F0 and complement the output to get the solution in a practical way. We will use that hint, hopefully. Let's see if it is useful or not together. So it's your function is A, B, C, D inputs, sum of min terms, 3, 9, 11, 12, 13, 14, 15, plus, this is how we write the don't cares. See, don't cares, and the small letter D for don't cares. 1, 4, 6. This is how you will get your questions in the exams as well. This is the terminology. And we just transfer this information, this truth table, into our K-map, Carnot map. 1, 0. Let's do this together. A, B, C, D, and okay, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, 12, 13, 14, and 15. Okay, this is how I placed my ones here. And then I will go ahead and place the x's here. It's in 1, and it's in 4, and it's in 6, right? 4, 5, 6. There. Okay. I think I'm ready to roll. So I will just what does the question tells us? Go from F0 and take the inverse for your benefit later. So let's go ahead and work with the zeros now. So if we are dealing with F0, it means that we can go ahead and use the min terms for zeros now for better use, and use the x's for our benefit as well. Let's do it. Let's try to do it. Okay, I hope I succeed here. Okay. Okay. This one. Oh, good. And how about it? This one, right? Great. So, do I need to cover this? No. If it is useful for me, I will do it. If it is not, I will not. So I don't cover it, okay? No need for this, because it is not a exact zero here. This is the trick, okay? Now, what is my F naught here? My F naught is, let me put the labeling here, A, B, C, and D. Okay, my F naught is, the blue one is B naught, D naught, B naught, D naught, plus the green one is A naught, B. But be careful, this is my F naught, not F. So I need to take the inverse of F naught to get the result here for F. And using De Morgan's law, you remember from the previous session, I guess, it should be something like this: B plus D and A plus B naught, A or B naught. Okay, it looks like this. So this would be your answer, and we also have taken the hint of the author into consideration as well while solving this question. Okay, so the algorithms that try to minimize the circuits are using this type of mechanisms for finding the optimum solutions. They're finding the all prime implicants first, then putting all essential prime implicants into solution, then placing the selected prime implicants with minimum overlaps for not all yet covered min terms. That's it. I mean, there are several algorithms for this. For this, but that's the basic idea. Okay, you first, define your prime implicant here. This one is essential, as you see, and this one is essential. Why? Because of this. Okay, this one is a key cell, and this one is also another key cell. So I place them right there in their positions, and they're essential. And the other ones are dependent on my selection. I can go for anywhere right here, but just minimizing overlap this time. That's it. That's how we do the selection. Okay, another one here, as you see. We first find the prime implicants, as we know, and we understand that, not x's, but we will focus on the ones here. This one is crucial. Other ones, they have an overlap. Do you think this one is crucial as well? No, because it's an x. It's not a 1, so I don't care about it. And I particularly place my essential prime implicant first here, this one, see? Then I select them with minimum overlap, this one and this one, for example, with minimum overlap between my variety of selection possibility between the other prime implicants. There are some soft computing methods for suboptimum solutions as well. If you have a large set of input variables here, one of them is espresso algorithm. It has been given here, but I will skip it for now. It's just doing some nice approach for minimization, but I will not go in detail about it now. And we will continue with multiple level optimization. Multiple level circuits are not 2-level anymore. They can be 3 levels or more. Okay, these are called multiple level circuits. Why do we need them? Why do we have them? Because they can result in even better cost. But is there a practical method like K-maps or something like this to find the optimum multiple level circuit? No, It's a bit tricky, so it needs experience and more soft computing methods, algorithms, I guess. And you apply some transformations to circuits for reducing evaluation cost. And you have 5 methods for this. The first one is called the factoring. Factoring can be summarized as like taking in common parentheses, like using the distributive law. In any sum of products or product of some expression, you take them in common parentheses. Decomposition is roughly separating, just defining some subfunctions or blocks within a Boolean expression. And substitution is just using a block in different parts of a Boolean expression. For example, using G in different parts of F, as given here. And elimination is the inverse of substitution, where you flatten or collapse the circuit. We will see the example. And extraction is decomposition applied to multiple functions. So you're using the same blocks in different outputs of the circuit. So we will see the examples. Now let's take a look at factoring first, like taking them in common parentheses. You start with this one, and you use this for here, and you go ahead and use this for here, common parentheses, what you do here. Then you go one more step, like this, go on with factoring, and you go on with factoring again here. What you have here in the end looks like this. And look, this one and this one are same. So you put them and use common parentheses again, you end up with this. You see, this is not a 2-level solution anymore. You see, it's 3-level solution. As you see, it's like the first level is something like this. You have AND gate into an OR gate. Oops, it looks like an XOR gate. An OR gate, and they're entering another OR gate here. See, this is your first level, this is your second level, and this is your third level. Something like this. And is it first level? Okay, anyway, it's more than 2. Okay, it's a 3-level circuit or something like this. Okay, that's the idea. And for the decomposition, those terms can be defined as functional blocks and can be used in the function separately. Like so, you can represent f as like this, e is b, and this, and the cost will be the same. This is called, this procedure is called decomposition, defining some blocks within a Boolean expression. And let's take a look at substitution. Substitution is just using the same block in different parts of the circuit. Like since you have E defined here like this, you use this block in different parts of the circuit like this. See, it is called substitution. All costs are the same, 10, and it's reducing our original cost, 2-level cost, from 16 to 10 here in those transformation examples. Now for the elimination, we begin with a new set of functions. Okay, this one is your sub block or sub function. This is also another block, and you put them here, and this is your output final Boolean expression. That's it. Now we first eliminate x and y from z. Okay, this is called flattening, collapsing the x here. You put them in their places, you expand them, and then flatten it, it becomes like a sum of product expression now. But temporarily, it's pretty interesting that it should it has risen the cost here up to 12. You see, so but gives us a new view for us to make a simplification here. Let's take a look at this. Just look at this. It is, as you see, it is C. Then this one and this one is what? C parenthesis 1 plus b, and it's c again, see, and your function is reduced to this, not b plus c. Okay, so how beautiful it is. Temporarily it raised the cost, but in the end it helps you with a brand new look. So the result is two-level optimization. It can happen, of course, and so you can keep in mind that it can start with any set of equations, not just with minterms or truth table, and also increasing the gate input cost temporarily can also be beneficial for seeing different types of minimization possibilities within the procedure. So it requires some expertise here. We're not dealing with some mechanical approach here. It's more like creativity. More depends on experience. More depends on how you see it. So it's a bit harder, but of course rewarding. So in the end, your final circuit will be much better cost, or much better, much less cost. And the extraction is using a common factor in two different functions, which reduces the cost significantly as well. It's a very nice trick for multiple level optimization. Look at this. Now you find a common factor and define it as a new function here. How is it possible? You take in a naught parenthesis here, b naught, d naught plus bd, and you have here is in c parenthesis naught d naught plus bd, right? You write this like this first, and you define this as a new function, and now it becomes like this. You don't need to build this part twice now. Building it only once is enough. You just put a while out for the other function. So it is AF and CF here. So A naught F and CF here. And the resultant cost is what? Since, I mean, the original one is 16, but this one is what? So it is a 2-input AND gate, 2-input AND gate. That's it. And you find the cost of this one. What is it? It is 2 connected to 2. It is 6. See? 6 plus 2 plus 2 is, for your final cost, is only 10 instead of 16. So it's much more cost efficient by using extraction. Okay, this was all about the circuit optimization. And in the next part we will be dealing with additional gates and circuits, like some complex XOR gates, XNOR gates, whatever. Okay, thank you for listening.